Thank you. Thank you. Welcome. Welcome. Welcome to Perimeter Institute in Waterloo, Ontario, Canada, and welcome to this Perimeter's Public Lecture Series. My name is Greg Dick. I'm the Director of Educational Outreach, and it is a pleasure to welcome everyone here. Those of you here in the theater and those of you watching online. Tonight's lecture will last approximately 1 hour and will be followed by a question and answer session. For those of you watching online, if you follow our Facebook and Twitter feeds and use hashtag #PILive, Dr. Damien Pope and Dr. Kelly Foyle are behind their keyboards with a team of researchers ready to engage in questions and discussion throughout the lecture. So use hashtag #PILive to access that conversation. And also, if you are online, get your questions in early so they can make it all the way to my phone in time for the Q&A at the end of the presentation. And now, it is my honor to introduce tonight's very special guest speaker, Dr. Pauline Gagnon. Dr. Gagnon was born in Chicoutimi, Quebec, and received her physics degree from the University of Quebec in Montreal. She received her PhD in particle physics from the University of California. She then joined a research team from Carleton University to conduct research at CERN and later became a senior research scientist at Indiana University until she retired in 2016. Dr. Gagnon contributed to the construction of a tracking device at the ATLAS detector, searching for dark matter particles in the decays of Higgs bosons and in the form of hypothetical particles called dark photons. Now retired from active research, Dr. Gagnon is dedicated to inspiring other curious minds of all ages to ponder the same big questions that she was fascinated by as a child. And Dr. Gagnon's popular science book, Who Cares About Particle Physics? Making Sense of the Higgs Boson, the LHC, and CERN, not only explains current issues in particle physics, but also explores the importance of fundamental physics in shaping not only our understanding of the universe, but society as well. And in tonight's lecture, Dr. Gagnon will explore the incredible and improbable feats of ingenuity and cooperation that have led to humanity's greatest experiments, and why such pioneering research, albeit impractical, in terms of everyday usefulness, has changed the way we live and is vital to our future. Ladies and gentlemen, please join me in welcoming Dr. Pauline Gagnon.
Thank you. It's great to be here. Thank you, Greg, for the invitation. Thank you, Perimeter Institute, for having me here. It's a great place. It's an honor to visit it. I had never had a chance before. And tonight I'm going to tell you about improbable feats and useless particles. And so to do so, I'll go through, whoops, I think we need to switch to the presentation. There we go, okay. And what I'm going to do first, I'll give a short introduction to particle physics just to make sure that all of you know what this is about. And then I'll talk about the people who are involved in that research and show the special management style that we have and how we manage to do such seemingly impossible things. And I'll talk then about how we work and how do we go about to find those particles. And I'll show them that the particles themselves are probably useless, and why do we do it? But you'll see that there are lots of benefits for society. And I'll conclude in looking at where are we right now and what remains to be done. So the aim of particle physics is to find the smallest building blocks of matter. And that would be a very simple thing to do if we were at Legoland. Legoland, that's where is in Copenhagen, because that's where they were invented, the Lego bricks. And it would be very easy there to tell you what are the smallest building bricks that made all matter around us, because everything in that museum is made with Lego bricks like this. So all I would have to do when nobody is looking, I would just break one of the exhibits, and we would see all the fundamental pieces flying around, okay? And you know, we would end up with a limited number, a finite number of fundamental particles. It's exactly the same thing in real nature, except that those building bricks are extremely small and we don't see them. But it works exactly the same. With a handful of particles, we can build everything we see around us. You know that any piece of matter, like a block of wood like this, is made of atoms. You know because we haven't told you. We have told you. But it's really difficult to see them. They're so small. An atom is 1,000,000 times smaller than a hair. This is the smallest object that has ever been photographed with a quantum microscope, and it's an atom that we have there with the cloud of electrons and all that. So an atom is about 10 to the minus 10 meter. So that's the scientific notation, and it's very concise. 10 to the minus 10 simply means that you have 0, 0, 0, 0. You move the decimal point by 10 position. So you have 0, 0, 0, 0, 9 zeros, and 1. So that's the size of an atom, 10 to the minus 10 meter. So that's really, really small. But that's not even the smallest thing, because an atom, as you probably know, inside there is also the nucleus, which is 10,000 times smaller. So if I was a nucleus, my electrons would be 20 kilometers away from me. Okay? And in between, it's just vacuum, emptiness. It's only because of electric repulsion that we don't go through matter. That's all that keeps us from going through the matter. So 10 to the minus 14 is the size of a nucleus, but the nucleus is also made of protons and neutrons. Inside the protons and neutrons, we find quarks. We find 3 quarks and gluons inside the protons and the neutrons. So, and those are so small, we don't even know their size, 10 to the minus 19. So it's 1 billion times smaller than an atom. So now, if I ask you from this picture here, what are the only particles that you see there that we cannot break any further? What would you say? The smallest ones? Quarks, yeah. Anything else? Gluons, although they're not there, but that's true. And there's another one that is there, the electron here. So those, the only fundamental particles that we have here are electrons and quarks on this picture. And with those, we can build everything that we see, all matter that we see here on Earth, but also that composes stars and galaxies everywhere in the universe. So how it goes is that if I take one up, there are different types of quarks. The smallest ones are the up and down quarks. The up quark has an electric charge of 2/3 of the charge of an electron, but it's positive, so plus 2/3. And the down quarks have a charge of minus 1/3, so 3 times smaller than the electric charge of an electron. So if I take 2 up quarks and 1 down quark, you see that's all the mathematics we will do here. So then you have plus 2/3, 4/3, minus 1, 3/3, and you get a particle that is positively charged. That's the proton. Fairly easy. If I want to make a neutron with up quarks and down quarks, with 3 of them, how would I make it? Yeah? 5 points for you. Yes, ma'am. So two down quarks makes minus 2/3, plus 1 up quark, 2/3. Then together they give a neutral particle. So you see, it's fairly simple to build up neutrons and protons with up and down quarks. And then from that, I can build the whole periodic table just by combining protons and neutrons in different ratios. For example, the lightest of all the elements is the hydrogen atom. Then you have 1 proton, no neutrons. In helium, we have 2 protons and 2 neutrons. And then as you go up in the periodic table, you just add always 1 more proton, and you change the nature of the chemical element. And we had just about as many neutrons as protons to make a stable nucleus. Then you had the same numbers of electrons around as you have protons inside, and you've got all the elements here. So you see, I can build everything that we have. Those 118 elements are all that we have on Earth, but also in the stars and galaxies, and we know that because they shine, and by looking at their light, we can see exactly which elements are there. So now it's getting to be very, very simple. We know that all matter is made of fundamental particles, just like at Legoland, I can build everything with a handful of different bricks. I can build everything in our universe, everything that is visible in our universe, with a handful of particles. In fact, we have 12 building bricks. So this now is, we have a nice picture of the material world, which we call the standard model. That's a theoretical model that explains how it goes. So the first principle of this model is quite simple. All matter is made of fundamental particles. And here they are, the 12 of them. They come in 2 families. The first family is a family of leptons, from a Greek word that meant light particles. And here we have the electron that you all know. The muon is very similar to the electron, except that it's 200 times heavier. But it also has a charge of -1. And the tau particle is 4,000 times heavier, but also is negatively charged. All of them come with a neutrino, a very, very light particle, and it's not until there was this experiment in Sudbury that we could prove that they had a mass. It was one of the 2 experiments that they did, and that's why Art McDonald received a Nobel Prize for that last year with a colleague from Japan. So we have those 6 particles. Neutrinos are, I brought one here just that you will all know that they really exist. So those particles, those cute little ones, come from the particle zoo. And it's a young woman from California. She was attending a lecture like this one night, a public lecture, and she thought it was so cute, all those particles. And then she decided to give them a personality, and she started the particle zoo. And now she's the zookeeper. And she makes us those. And I'll just pass them around so you can see what they look like. And you can send them to the back, and someone at the back maybe can pile them up in the corner. We'll pick them up at the end. So the neutrinos are quite sneaky, and that's why she put them with a little mask, because there are billions of them crossing this room as we speak, and they don't even stop to say hello. So it's very difficult to interact with a neutrino. We're very lucky to have one here. So we have the leptons, that's a family. The other family here is made of quarks, and we call this family the hadron family. The name will come back later with the Large Hadron Collider. So hadron, it's any particle made of quarks. The leptons, they don't make composite objects, but the quarks, they mix up like we saw with protons and neutrons. So I already mentioned the up and down quarks, but there are also the charm and strange quarks. Strange quark was the 3rd one to be found, and all particles that had the strange quark had a strange, long lifetime. And that's why it got this name. And once it was started, then so the next one, they called it charm. Why not? Then it was truth and beauty, but finally we renamed them top and bottom. The top particle is the heaviest that has been found to date. And so we have 6 quarks in the family of hadrons and 6 leptons. What is really surprising is that to form all matter that we see here, we only need the first row of particles. It is as if I give you a nice construction set for Christmas, and it's full of blocks, but there are some blocks that you never use. It's a funny construction set. Not only that, some parts are really small, and others are 4,000 times bigger. So it's a weird construction set that we've got here, and we don't understand why it is so. So, just like in a construction set, so if these were my particles here, Some construction sets came with connectors. You could connect those things together with connectors like that, rigid lines. There were some, what was it, Meccano, for example, had things like that. So in our case, what binds those particles together, it's not a static bond like this, but rather something dynamic, and I'll show how it works. We say that these particles interact with each other by exchanging other particles that we call bosons. Bosons, you've heard that before. So the bosons are associated to the fundamental forces of nature. So we have the gluon, as its name indicates, gluon from glue, and that's what binds the quarks together inside the neutrons and protons and keeps them together. And we have the photon that is associated with the electromagnetic force. This one is associated with a strong interaction, we call it. The mechanism by which the sun burns its energy is through the weak interaction, and it goes by emitting 3 different particles, 2 W's, W plus, a W minus, and a Z, a neutral particle. There's the gravitational force that you all know, and very recently gravitational waves were detected for the first time after it had been predicted 100 years ago by Marcel Grossmann and Albert Einstein. So, but we have not yet found a particle that is associated with it, the graviton, but you still find it in the particle zoo, but it's just hypothetical still. And finally, the Higgs boson, which is related to a new field that was postulated very recently. So, our standard model, 2 very simple principles. All matter is made of particles, and they interact with each other by exchanging particles associated to different forces. The way it goes, it's a bit like if we have 2 skaters, and they evolve on separate trajectories, and one of them would come and toss a heavy ball to the other one. It will make this one recoil as well as this one as well. Both of them will change their trajectory. We could say, oh, a strange force. If you look from far, you might think, oh, a strange force acted on them that made them deviate from each other. But in fact, it's because they tossed something heavy at each other that made them change their direction. So the forces are not static forces, but it's an exchange of particles. So it's very dynamic. Okay, so in the 60s, we had found a lot of fundamental particles, and we have all them listed here in this little particle physics booklet that every particle physicist, everyone in the building here has a book like that, and all the properties of the particles are listed there. So in the 60s, it was very complex until someone came up with the quark model, and then we could see that all those particles were in fact just composite objects made of various combinations of the 6 quarks that I showed. So I'll pass this around too. It's interesting. So you have all the properties of all the particles that we know. There are 238 of them, I think, that we have found, but it boils down to 12 grains of matter and 12 grains of force, if you wish. But in the 60s, there was also another problem that was major, was that nobody knew where these particles obtained their mass. How could the particles acquire their mass? In the laboratories where we had seen them, we could see that they had a mass, but in the equations that theorists were handling, the mass appeared nowhere. So it was a big mystery. And finally, a bunch of theorists had done a lot of work before, and then came François Englert and Robert Broux, 2 Belgian physicists, 2 theorists, who proposed a new mechanism to explain how particles acquire their mass. And he said that this mechanism implied the existence of a new field, and that particles would acquire their mass by interacting with this field. I'm going to explain all that clearly in a minute. Just to say that François Englert and Robert Broux were the first 2 to mention that, but the name that you know better is the name of Peter Higgs, a Scottish theorist, who published his paper a month after the other 2. And what happened to him, it was first rejected by the editor of the journal where he published it. So he was really bummed out, and he thought, well, the editor told him, totally useless, your theory. It doesn't come with any practical projections. There was nothing that it predicted, no predictions. So Peter Higgs said, yes, it comes with a new boson. So he modified his paper, submitted it to another journal, but this time he mentioned the existence of the new boson. And that's why the Higgs boson is named after him, because he was the first one to mention it. But in fact, the first two to talk about this mechanism, they developed these ideas at about the same time. And in 2013, François Englert and Peter Higgs received a Nobel Prize for that. Unfortunately, Robert Brou was already deceased and could not receive it. So what did they do exactly? So they said that there was a new field that gave mass to particles. Bon. Okay, so that's probably what we see in the prairies here in Canada, but a field in physics is something different. A field is simply something that modifies the properties of space around it. For example, a magnet. If I put a magnet here, if we look around it, we don't see anything different. Right? But go and spray some iron filing around it. Much better if you first put a piece of clear plastic, it doesn't stick to your magnet. But you can do that, and then you will see the filing, the iron filing grains align along the lines of field like this. But don't forget the plastic sheet. You get a mess otherwise. So what the magnet does, the magnetic field modifies the properties of the space around it, and other particles that are able to respond to that will behave differently. So, three other concepts that I'm going to define. The concept of mass. In physics, we say simply that it's the resistance to motion, or the resistance to the change of your state of motion. For example, a huge ship like this has a huge mass. So to get it going, you have to give it a lot of energy to change its state of going from rest to going into motion. So it has a lot of resistance to a change in its state of motion. Energy and mass are equivalent. It's this very famous equation, E equals mc squared. Who did that? Who did that? No. It's Albert Einstein and Mileva Maric-Einstein. They did everything together. And, it's very clear. There is a whole chapter on that in my book. And there is also a huge biography that just came out on Mileva Maric-Einstein, published in 2015. There is no doubt about it. But this was a brilliant thing. These two were working for about 18 years. They worked together. They were exchanging ideas and discussing and writing and reading together. And they did everything they did until 1914 together. So E equals mc squared is this principle that states that energy and mass are equivalent. So E represents energy, m the mass, c squared is just the square of the speed of light, and it's a conversion factor. And it's just a bit like me, because I live in Europe now, I live in Germany, so in my wallet, I was going to bring it, but I have euros and I have Canadian dollars, okay? And the two are two different forms of the same essence, money, but shown in different formats. So, and there is an exchange rate, which is never good for Canada, but there is an established exchange rate between the two, and you can transform one into the other one. E, we can get energy and produce some matter from it. That's what we do every day in laboratories like CERN. I'm going to show that in a minute. Or we can take matter, like in a nuclear reactor, and turn it into energy. But the two are two forms of the same essence, and we can look at mass like congealed energy. Last concept, it's energy conservation. So energy can take several forms, but it's always conserved. So for example, if we represent the energy with a liquid, a red liquid, I have a container here and I have a certain amount of energy. I can pour it in two different containers. For a fundamental particle, it can have energy in two forms: movement, so kinetic energy, or associated to its mass, congealed energy. So if I start with a certain quantity of liquid, I can pour it in the two containers, but the total remains the same. Okay, we don't lose energy. Okay, so back to the Brout-Englert-Higgs field. How does this field generate mass? Well, if a particle was to go from point A to point B, in the absence of this field, it would just go at the speed of light on a straight line and reach point B. Okay, I do it a bit slowly. So you can see it goes on a straight line straight to point B. And at this point, all the energy of this particle is in the form of movement. It's massless, and it can go at the speed of light. There's nothing to hinder its motion. But right after the Big Bang, someone turned on the Brout-Englert-Higgs field. I think it's something like 10 to the minus 25 seconds after the Big Bang it appeared. Before that, there was nothing, but the Brout-Englert-Higgs field appeared just after the Big Bang. And then when the space is filled with this field, then particles will start to interact with the medium. They will start interact, and they can no longer go on a straight line. Exactly as if there is no Higgs field, it's like crossing an empty room. I can go as fast as I want, but if I try to go across the room here, of course I'm going to interact with all of you, and I won't be going as fast, or just even stopping to talk with you. So the particle here no longer goes as fast as it was, so there is less energy associated with its movement, so less kinetic energy. Where did the rest of the energy go? Yeah, that's it. I was giving this lecture in a high school some very lost island north of Scotland, and a little girl, her face just lit, and she said, "It's mass." And then she saw the whole phenomenon. It was really nice. So it's a weird thing, but that's how the mass appears. It simply is converted as the particle interacts with the field. Some of its energy is transformed into mass. So I have said nothing yet about the Higgs boson. But we could say that you know that a wave at the surface of the ocean, a wave is a perturbation at the surface of the ocean. If you give energy to the ocean, be it by the attraction of the moon, or from a tsunami, or from the wind, you can create waves. So you give energy to the ocean, and it turns into a wave. We could compare the Brout-Englert-Higgs field to the surface of the ocean, and the Higgs boson would be like a wave on this field. So waves are excitations of the ocean surface, and the Higgs boson, we get them by exciting the Brout-Englert-Higgs field. So that's what we did at CERN, and we proved that the theorists were right. So in 1964, these three theorists had told us that there would be this special field. But it's a bit like if I'm here and I'm telling you, look, I have an aquarium here, a glass aquarium, and it's filled with water. Do you see the water? No, okay. So fair enough. So I can tap on the pane, the glass pane, then you'll see wavelets at the surface of and then you'll say, yes, yes, I see them. So that's exactly what we did. We went and we excited the canvas of the universe. We created those waves. Those were Higgs boson. So I have one of them here for you. So here we go. You see, it's quite heavy, this one. And to compare it, here is a photon, which is a particle that does not interact with the Higgs field, the broad angular Higgs field. We don't know why. But this one doesn't have any mass. And it's one of the rare particles with gluons that don't have mass and they can go at the speed of light. So here is the photon. Okay, so before I tell you how we did this, I'll go and talk a little bit about where was the Higgs boson found and who did that. So it was found at CERN. CERN is the European Laboratory for Particle Physics, and we have 12,000 researchers there, mostly physicists, but also engineers, who come from 63 different countries. It was first founded by UNESCO in 1954, and now it has 22 member states. Mostly it's all of Europe, but also now they're recruiting outside Europe. So Israel is the first country to join. But there are all these countries, for example, Turkey, Pakistan, Ukraine, and India, that are in the process of becoming new members. So here is the map. In blue, here are the member states, including Turkey is in the process of becoming, and Israel is there. India now should be in blue. And there are countries that are in green. Those are special observers, so they can attend the meetings of the CERN Council. And the other countries in red, like Canada, pretty much all of South America, and several other countries, are the participating countries, 63 countries in total. Canada sends 174 people to work at CERN, researchers. But in fact, not all of them are Canadians. In fact, of the people, so Canada hires 174 researchers, but in total at CERN, there are 154 that are Canadians. So like me, for example, I'm Canadian, but I was working for an American institute. So we come in total from 102 different nationalities. And if you had been at a physics meeting about 100 years ago, that's what it would have looked like. There are 29 people here, and 17 of them had a Nobel Prize. So all of you will have recognized Marie Curie and Albert Einstein, but all the big names, Heisenberg, Bohr, De Broglie, all these people are there. But today it looks quite different. It's much more diverse, and it's quite important, but it's still not completely diverse enough. For example, it started as a European lab. So, of course, 3/4 of the lab come from Europe, a big fraction from Asia, but it's mostly India. China has only a handful of researchers at CERN, and North America is about 1/8 of the total. Together, there are about 17% of women at CERN. So roughly, we can say that at CERN, 80% of all scientists are male and 80% are white. So it's still not as diversified as it could be, but it's changing. If we look at the distribution of all the people under the age of 35, just to see how it could evolve, then you can see that Asia is going to take a bigger part, and North America as well, and a little less from Europe. But still, Africa is not very well represented, and women, it will be barely 23% in total. So we need to do a bit more to bring more diversity. And you will see in a minute that diversity is crucial because we rely on creativity for our work. And you need to have people with different ideas, different background, and all that. I'll tell you a story in a minute about that. So here are some of the people working at CERN. This is the part of the CMS collaboration. We have on the Large Hadron Collider, the LHC, we have 4 large experiments, Atlas, where I was working, and there are about 9 institutes from Canada sending people there. I said 174 researchers. CMS, another very large group, each of them has about 3,000 scientists. LHCb and ALICE are 2 smaller experiments, and they each have 1,000 researchers. And we look for an array of different phenomena, and we all cross-check each other. That's why we have several detectors, is to make sure that what we find is not just a mistake, but it's really what was happening. So the Large Hadron Collider, the name comes large, easy to see, 27 kilometers around. Hadron because we have protons inside the collider, and collider because we bring those protons into collision to give us sheer, pure energy which will materialize and form new particles that we want to study. So that's the Large Hadron Collider. If you come, to give you a scale, here is the Geneva airport, and here is Lake Geneva, the Alps in the back. If you come from above, you won't see the ring because, in fact, it's 100 meters underground, and there are 4 access shafts leading to each of the experiments, which were built inside caverns underground. So we have 2 types of 2 tools to work with. We have the accelerator, which simply accelerates the proton, brings them into collision. The energy that is released materializes. It forms very unstable particles that break apart, makes like mini firework, and all sorts of things fly apart. And we have detectors that are huge machines that are built around those collision points. We have 4 of them. We have those detectors that they have the shape of a cylinder with 2 end parts to be completely hermetic. And it's made of several layers. Each layer gives us different pieces of the information. So the accelerator accelerates the particle, and the detectors detect what comes out. So the more energy we put, the larger the particles that we form, and then the larger are the chances of finding something that has never been seen before. And how it works is a bit like this. I'm going to show this short animation movie. So we have here protons that are in the beginning of the accelerator. So they go and they get accelerated. Every time they reach the maximum energy in this small accelerator, they go to the next stage. So this one was just 100 meters around. Here it's 7 kilometers. And it finally enters the Large Hadron Collider. And then we can see inside, it's a tunnel, like a subway tunnel. And inside we have this pipe, which is a vacuum pipe. And it has large magnets around to bend the particles on their trajectory, the trajectories of the particles. Here you see the 3 quarks inside the protons. So it's not just one proton. Normally it's 20 billion protons come from the right, 20 billion from the left, and they meet smack in the center of the detector, and they produce a mini firework so something heavy and unstable is produced, breaks apart, and we catch all the fragments with our detector, which is made of several layers. Each one will give us part of the information. So the detector acts like a giant camera. It's made at the center here is what we call the trackers. So we try to find where each fragment came from. Around it, we have several layers called calorimeter. We measure the energy that each fragment had. And we also have large magnets around that to curve the trajectories of the particle. Then we can measure which charge they have, and also how much, at which speed they were coming out. So we can all measure that. So we get lots of information. And then it's a bit like different particles will leave different tracks in the detector. A bit like animals walking on fresh snow will give different tracks. And someone with a slightly trained can tell the difference between the track of a rabbit, a deer, or a skier. And it's just as clearly, it's very simple to tell the difference between those tracks. So we can identify each fragment and then reconstruct what happened in the center. And then we get images like this. And when we see something coming out very, very quick, very fast, then even with our magnets, we can not bend their trajectories. So these, we know that they are really fast particles. And all the other ones, it's because it's like, it's not one proton coming from the right and one from the left like it was shown, but billions coming in each direction, like two swarms of bees. And they just cross each other. So some of them will make head-on collision, rarely will have a head-on collision with a lot of energy, and that's what we want to find with very energetic tracks coming of that. And many others will just barely graze each other, and they will produce particles that are not very energetic, and those, with the magnet, you see, we make their trajectories curve, and they just disappear. So we're not interested in that mess here. We just look for the very energetic tracks, and we have very fine trackers. We can look precisely from which point they come, and then say only those 4 came from this particular collision. In general, we have between 40 and 60 collisions at the same time. It is as if you take a picture. I had a camera like that, I don't know if you ever had one, that didn't move properly the film, the pellicule inside. So sometimes there were several pictures that were superimposed. Sometimes it was interesting. Most of the time it was annoying. But that's about the same thing we get here. So where do we start to build those detectors? How do we plan all this? That's why I'm going to tell you more about our management style and all that. So we start with the ideas of theorists, like the people working here at the Perimeter Institute. The theorists will tell us what they think might happen. So for example, we were looking for the Higgs boson. Had been postulated in 1964. We had to look till 2012 to find it. It took nearly 50 years, 48 years to find it. So they were predicting, for example, that gluons coming inside each of the protons would collide, create a Higgs boson. There would also be top quarks with that, and all that would decay into a variety of particles. In general, very few particles are stable, and so in our detectors, we only find electrons, photons, protons, pions, muons, so a handful of particles. But we knew that our detector had to be sensitive to a variety of particles. And we wanted also to have a high granularity to be able to tell the difference, that there were 2 particles and not just 1. And other possibilities that theorists were telling us, we could also produce Higgs boson. Sometimes when 2 quarks would come, they would just barely graze each other, exchange Z or W boson, and these would fuse together to give a Higgs boson, and the initial quarks would just continue barely changing their direction. So that means that these quarks we would find really close to the beamline. So we wanted our detector to be very sensitive, close to the beamline, to find that kind of things. So we had to make our detectors sensitive in all directions, and they had to be very fast and precise, because we get collisions every 20 nanoseconds. So, and we're like tourists in vacations. We take pictures like mad, every 20 billionth of a second, we take a picture and picture. And then we go home and we have to sort out what is interesting. We do some sorting out at the start. We retain about 100, 200 pictures per second, but still, you have a lot of sorting out to do afterwards. So that's what we were doing. And some other theories that they were predicting, for example, the case of a supersymmetry, where a supersymmetric particle could come in, would always decay into another supersymmetric particle, like the black tracks here, and at the end, the lightest supersymmetric particle would simply escape from our detector. So we wanted something that was really hermetic, such that even a particle that is not interacting with the detector, but that escapes our detector, would be found. We know how much energy we should find, because you see, they come, 2 particles collide like this, so they come along this axis, and then there are particles, fragments flying in all directions. So when we look in that plane, let me turn it for you. So if we look in that plane, we know that all the particles, all the energy and momentum must sum up to 0. So if something escapes, we can see it from that principle. Okay, so those were the broad qualities that we wanted for our detector. So the first step is to make a technical design. That took about 5, 8 years, I'm not sure. The collaboration establishes what needs to be done. Then the whole project was divided into sub-projects, and each participating institute signs up for one of those projects. So for example, the group at Carleton University, they signed up for the hadrometer. So it's a calorimeter that will measure the energy for all the hadrons that were coming in the detector. And oftentimes, several ideas, different groups say, oh, I will do also a calorimeter, but they have a different technology in mind. So they will pursue different ideas in parallel, and we must debate to see which one is the best. So everyone has the right to say what they think. So everyone can suggest ideas or methods, but then we must prove which one is the best one by debating, showing our results. We base our results on prototypes or on the simulations done on the computer. And the best method will be selected based on its merit. And the common goal of the experiment, that is being able to find the Higgs particle, dark matter, supersymmetry, whatever, all this is decided. That's the main goal. And even if one person disagrees, one of the coordinators disagrees, the common goal has the last word. The decisions are made by consensus, so we spend countless hours in meetings. We're in meetings all the time, so people present their work, what they have done, and we can comment, we can say, but did you think of this or that? And then the other one will say, no, I had not, and then you go and you improve your thing. So, and because we have so many meetings, everybody comes with their laptop, and they keep working on their own things, and when there is something that is of interest to them, then they can pay more attention or comment. But we spend so much time there that everybody brings their laptop. So there is no top-down hierarchy, and that's the big difference on how we work. Nobody is there telling us what we have to do. For one very simple reason, nobody knows what we have to do. Nobody has the whole idea, so nobody would be able to do it. There is no director, there are only coordinators, and everyone can choose what they want to contribute. So for example, if I'm good at tracking, I can say, okay, I'll try to build this detector, so our group works on that, and then we compare with the other groups that have different ideas, and we see in the end which one is the best. So everyone does as they please, but it's not a free-for-all. It's a bit like, so we have this technical design that tells us we need this part, that part, that part. We all agreed on that. Whoops. I don't know what I did, sorry about that. Let me fix this. It's like a huge picnic. And when I organize a picnic, I don't like so much dessert. So I make sure that there is enough, of salty stuff, savory stuff. So, when you coordinate a picnic, you make sure that there's enough to drink, enough main dishes, chips, bread, cheese, desserts. So then you break everything in projects like that, and everyone brings, I'm good at making a salad, so I'll bring a salad. And I've seen your last dish, why don't you bring the beer? So you give everyone according to their taste and their resources and what they are better at. And each person must figure out how to contribute, and everyone is responsible for the success of the whole project. We must find what we can do, but we're also responsible for everything. So we have a common goal, which is we want to increase the human knowledge. We want to answer all those questions we have. Is there a Higgs boson? Is there supersymmetry? Is there dark matter? Is that all those things? So we want to answer our fundamental questions. And the individual benefits is that we get to do some very interesting projects. We participate, we build things that have never been done before. It's a huge challenge, and it's very exciting. There are no financial bonus, no compensation. And you let people do what they want, and they give their best. It's really amazing. You don't force anybody, but everybody has a chance to really give their best, and it's really nice. The whole project needs everyone's creativity. And so if one group fails, like there were 3 groups in my project for this tracker, and there was one group, they were really, really unpleasant. The head of the group was particularly unpleasant, and he had hired a bunch of unpleasant people. So they were awful and incompetent. So they were really, but then at the end we had finished, the 2 other institutes had finished. We could not just stand there and say, nya, 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 nya. We could not do that, because if they didn't bring their third of the project, our detector was useless. So we had to go and help them finish. That's the only way we can do it. What we want to have answers to our questions. The only way is to build those huge machines. And so if someone doesn't do his or her job, we have no choice. Even if we hated them, their guts, we had to go and help them. So it's a very special way. So we must help each other, but we also all compete with each other for the jobs, the permanent jobs. Most people are postdocs or graduate students and all that, and there are not faculty positions for everyone. So it's a very special relationships we have with the others, but we must collaborate. That's the bottom point. And when there is success, everybody is celebrating together. Like here it was at the start of the LHC, in the LHCb control room, and they turned on the thing and everything was working, so everybody is rejoicing. And the funny thing is that we all volunteer for the most horrendous job. I volunteered to test over 110,000 wires. My father-in-law asked me, what had you do before to deserve that? No. So but at the beginning of the project, I was given one of those modules, and I had to figure out how it works. So I had a little power supply, and I had a bit of gas, and I was trying to make it work. And it was far from being obvious. And then 18 months later, that is what my lab looked like. And no, we were just testing modules left and right. The modules were built in the US in 3 different sites, and then they would come to CERN, and we would try to test them to make sure that all of them were up to standards and repaired the ones that were broken. And we were, essentially, there was myself and an engineer, and then we had a few other people who joined, graduate students in the summer and all that. And at the beginning, this engineer, I was trying to tell him what to do. I had no clue how to proceed, and we were absolutely overwhelmed. And it simply didn't work. First of all, he did not understand French or English. He was Russian. So we really had difficulties communicating. But then I figured out that the guy, when he wanted to explain something, he could draw something magic. So we would draw for each other, what we needed. And then I let him go. His previous boss told me, just let him go, you'll see. And the guy started doing miracles. He was not there from 8 to 5. He would come sometimes at 10 at night and stay all night and do his work. But then, he did the way he wanted it to do. He wanted it to do it, and then he did much better than when I was trying to tell him what to do. So, for example, we had this detector that had straws, 1.4 meter long, with a small electric wire in the center, no bigger than a hair. And we had to make sure that they were perfectly centered and the right tension and all that. And so he had sometimes to retrieve some of those wires from inside there. He was so brilliant, doing all sorts of tricks to do it. It was amazing. So it brings out the best out of people because you let people do as they please. And there's some good examples. For example, Maria and Giuseppe Fidecaro, I guess you got it, the name. Giuseppe got hired at CERN in 1954. He was one of the first ones to be hired. Maria came along, but it took her 2 years before she got a paid position. So she worked there for 2 years without pay. But even to this day, 63 years later, they're still coming to work every morning, 8 o'clock. You see Maria coming. She's very old now. But I had noticed her. Now, every lunchtime, I could see them in the cafeteria, and there were four older Italian like this, and they were just discussing, and food, and hands were flying. It was really amazing. But so people really are passionate, and that's really what makes the difference. And here in the end is our detector. The Atlas detector is a gigantic machine. It has 4,000 kilometers of cables. That's the distance, I believe, between Vancouver and Nova Scotia or something like that. 4,000 kilometers of cable. Each one of them had to be measured at the proper length, fitted with the connectors, connected at the right place. And then when you finish another part of the project, you just hope that someone would not come around with a ladder on his shoulder and wipe that, which happens sometimes. Literally, I've seen it. The detector is 7,000 tons. 7,000 tons is the weight of the Eiffel Tower. But the Eiffel Tower is just rusted steel, whereas this is all tiny, high-precision things that were all handmade. Like my friend Monica Dunford says in the movie Particle Fever, it's like a Swiss watch on steroids. It's unbelievable, the complexity of this thing. The best job I did on the detector was to go and vacuum on it, because they were asking for volunteers to vacuum, and at home I'm not the one, but I was there, and we had a small vacuum cleaner, like I saw someone this afternoon here vacuuming. It was nice. A vacuum cleaner like a backpack, and we went everywhere inside the detector to remove iron filing, retrieve screwdrivers that had been lost, and we found vodka bottles, we saw all sorts of things. It was very interesting. And then we could turn on the magnets without a tool, screwdriver puncturing something else, or iron filing, or a screw blocking something. So, giant machines, it's 6-story high. So this is called the giant, the big muon wheel. That's a special detector for muons. And this guy there is trying to make a selfie. So how did we manage to make it work? That's the most amazing thing, is that we turned it on and it worked. That was the most amazing thing. Everybody was just flabbergasted. How did we manage to make it work? It's because we are so motivated. And this motivation comes from the scientific curiosity. We want to have answers to our questions. Since I was 8 years old, I was saying, I want to know what matter is made of. I don't know where I got this idea, but that's what I wanted to know. And so I'm still at it. And we worked on this project for 15, 20 years, so we wanted it to work. And when there is success, like after the discovery of the Higgs boson, these were the people working directly on the analysis for the Higgs boson. Of course, the success is shared. Every paper that we publish in Atlas or CMS or any of those collaborations are signed by 3,000 names. And nobody has their name at the start. It's just alphabetical, So there is someone AAD, that's his last name. He has a bit more chance. He's always the first author. But it means nothing. All it means is that we need 3,000 names because these 3,000 people built the detector, did the data acquisition system, took the data, analyzed it, all those tasks. So we needed the contributions from everyone, and we acknowledge that with every paper. So why do we bother? Why do we bother? Because it was a lot of work. We will probably never find any practical application for the Higgs boson. Its lifetime is about 10 to the minus 22 seconds. You have to get up goddamn early to be able to do something with that. So the Higgs boson, probably useless, but it's just like about 100 years ago, Faraday was in his lab and he was working with electromagnetic waves, and the equivalent of the Minister of Finance came and he asked him, what are you going to do with that? Faraday said, I don't know, but I'm sure you'll find a way to tax us on it. And we all pay taxes on the mobile phones, the waves that we pay for and all that. So, but we do it, mostly the scientists do it because we won't have answer to our questions. We want to increase the human knowledge, to understand what is out there, where do we live, what is this world, this universe that we inhabit. But the reason why governments finance it is because it develops the technology. And the technology is what is the motor, it drives the economic development. So that's why governments take your money, your tax money, to pay for that. It's because it pays off. Every dollar that you invest in research, I know Harper had got that completely wrong, but every dollar that you invest in research comes back to you 10 times bigger. So, and CERN, for example, has a technology transfer office, and they try to find the best applications, and they look for industrial partners for that. The third reason is that we train highly qualified people who go and then participate in different things. Like one of the postdocs was with me now, she's at Statistics Canada. And her husband is doing something on the distribution of large, with optic fiber, large networks with mega data transfer and stuff like that. So we try, we train people, and we also contribute to world peace through international collaboration. On this picture, half the people are from Israel and the other part from Pakistan. Those two countries don't even have diplomatic relationships with each other. And these people had to work together, and they got to know each other, and they got to make friends with each other. And after a few weeks, they started doing field trips, going to Paris to see the Eiffel Tower and other things like that. So it really gives us a chance to see how the other ones are. Like I said, 102 different nationalities. I sure have a few good recipes now. And the benefits are huge. The benefits, the best thing that CERN gave to humanity, it's not the Higgs boson, but the World Wide Web. It has completely changed the way we work and live, and it allows the dissemination of knowledge and all that. Telecommunication, that all comes from the development of electromagnetic waves done 100 years ago, mobile phones, the electronics and computers. We learned about the electrons, semiconductors, and all that. So physicists do the research, the fundamental research, and then we need, of course, talented engineers and technicians to put that into applications. Medical imaging, that comes directly from particle physics. All those techniques of CAT scan, MRI, radiography, and all that, it all comes from particle physics. One of them, a new therapy, is called hadron therapy. So we take hadrons, particles that are built with quarks, like, for example, protons or carbon atoms. And it's much better against cancer cells to fight tumors than X-rays used in radiotherapy. You see, here is how much energy is deposited in the human tissue and at which depth inside the tissue it goes. And you see that with photons, you deposit a lot of energy all the way along, so you burn lots of healthy cells along the way. Whereas if you were to use protons, you can tune its energy to deposit the maximum of its energy at a specific depth. So this is much more powerful. So if you have somewhere in, the liver, kidneys, huh? the livers, then you know exactly where it is, and you tune the energy. And CERN has participated in that, and other labs as well. This is a center that is now in operation in Italy. That's what the patient sees, and that is what is behind the wall, the accelerator for those hadrons, in fact, protons, that was built at CERN. But it's not behind a glass window. Huh? I don't want to scare the hell out of people there. And just about all the best things come from fundamental research. So just to finish now, have we already found everything? That's a good question. I see that there are several young people here, so you might think, oh, I was born just 30 years too late. No, not at all. Everything that I talked about today is what we call visible matter, and this accounts for only 5% of the content of the universe. Most of the content of the universe is in the form of a certain type of energy that we know nothing about it, that we call dark energy. We know very little about it. And it accounts for 68% of the content of the universe. And 27% is in the form of a type of matter that doesn't emit light, and that's why it's called dark matter. So it's much more prevalent than matter, but we have no idea what this is. So all the particles that I have shown earlier is just, the visible part of the iceberg. So those particles compose everything that we see coming from in galaxies and stars and everything around us and on Earth. But most of what is there in the universe, we have no idea what it is. So for the young people here, are still students, we have figured out 5% of the content of the universe, so 95% is still to be explored. So the best theorists, like this guy here, John Ellis, with his assistant, Mademoiselle Mumu, is here hard at work. And theorists here have probably written a sizable fraction of those papers that you see here. Everybody is trying to find what could it be next, because we're just explaining a small fraction of what is out there in our universe. One way to look for new things is by looking at an excess of events. So theorists will tell us, for various processes, how many events we should find. So here's the number of events we should find and how much energy they should have. For example, when we look at all the events that we find in our detectors with 2 photons, and we look at the energy, the combined energy of the 2 photons, this is what theorists tell us should look like. It should look like the red line. But the black dots are what we have found with our detectors. And here you see it's a logarithmic scale. So we found a lot of those with low energy, not so many at high energy. But what was surprising, we saw an excess here, something that was absolutely not expected. So, in physics, everything follows statistics. So it can sometimes be a little more, a little less. We don't get too excited with something like that. It was first shown at a meeting in December 2015, but where everybody lost their breath was when so there was this excess there. The other experiment, CMS, showed the same thing at exactly the same point, except they had a little less data, so it was not so precise. The detector stops for 3 or 4 months every year for annual maintenance. So they showed that in December, just when we closed the detector, the accelerator, and then it only restarted in April or May, and then we had to accumulate a lot of energy, and everybody knew that the results would be shown on August 1st at a major conference. And then what was shown was that the effect had disappeared. And everybody was heartbroken, because we really thought we had at last found something. But in the meantime, theorists, like the people here, wrote 554 papers, 554 ideas that were all calculated and all that, to explain what it could be. And all of them were valid, most of them, and they just went like crazy. It was a complete frenzy. And on August 1st, it was shown that there was nothing, but a few people just couldn't let go. Well, it was very, very disappointing. But this goes by telling us that, here, the first 150, I compiled what was it that people were proposing. And essentially, there were lots of them that were just kind of a safe bet. They were describing the properties of a new boson. But there were all sorts of theories that were shown: supersymmetry, that it was a particle of dark matter, a 2 Higgs doublet model, new gauge theory, hidden theory, all sorts of things, axion Z. There were all sorts of crazy names, and it was pretty entertaining. But tons of ideas, and nobody knows which one it could be. So there's still lots of leeway, and we absolutely need an experimental evidence to figure out what it would be. So in short, we're stuck. We are really stuck. Without a new discovery, you see, theorists are going in all directions, and nobody knows in which direction we. Theory and experiments always go hand in hand. Sometimes the theorists predict something, like the Higgs boson. We looked for it for 48 years, and we finally found it. Other times, we find things, and theorists can explain what it is. So we work together, but now the theorists are really stuck. They need a hint to figure out in which direction to go. So everybody we're trying to find new particles that would reveal the secret passage to the bigger theory. Because we know that there is more than what we know. The standard model only explains the visible part of the content of the universe, and 95% is left out. So, to summarize, 3 take-home messages. The first one is we can achieve incredible feats by getting the best out of highly motivated people who are allowed to do as they please. And many industries now are trying to apply this model, and it really works. You let people come when they want, they let them take as much vacation as they want. We don't have so much vacation, but anyway. But people decide for themselves, and they give the best because they want their project to be a success. There will probably be never any application for the Higgs boson, but fundamental research drives economic development, and it has completely changed the way we live. And any new particle or new phenomenon that we discover from now on will revolutionize our understanding of the universe. So that's a thank you on this, and if you want to know a bit more, because it was quite fast, if you want to know a bit more on all these topics and on Mileva-Maric Einstein, you can have a look at my book, and I'll be offering it and signing it here in the atrium. Thank you for your attention.
All right, let's open the floor to questions. The microphone is right there. I see there's bright lights, but I see feet. My phone is in the green room. Go ahead.
Thank you.
I had heard that it was the collider was going to be recalibrated, and they were going to be looking for data related to the 95% that hasn't been seen. And I'm just wondering if you could comment on that, what they're doing, and maybe even comment what experiments you would like to see them to do to find out more information.
Well, my understanding how it's going on now, we operated the accelerator at low energy at the beginning, 8 TeV, tera electron volt. And then we increased the energy to 13 electron volt. And every time when you put more energy, you can make bigger particle. And so you have a chance to see new things. So we just went to 13 TeV in 2015, I believe. And we were hoping that something would jump to our face, but we have not seen that. So now we are in the process of accumulating billions of events, sorting them all, and in fact, it is as if we have landed on a new island. We're hoping to see, strange structures that would reveal the presence of special people, but we have not seen anything. So now we're turning every leaf, every stone, and looking for something. We are always looking for the dark matter in different ways. There's so many different possibilities that are explored, and that we have always done that all along. So this will stay like this. The next step for the Large Hadron Collider will be to go not at higher energy, we have reached the peak energy, or almost, but it will be at higher intensity. So we will get more and more data, and we hope to find very rare processes, but that's how we proceed. And there are other experiments, like for example in Sudbury, there are several experiments that are looking for dark matter. Some are in process, others are in construction, so we should also keep your eyes on Sudbury. There are great things will come from there.
Could I ask a related question? Mentioned dark photons. Could you just explain kind of simply what a dark photon would be?
Dark photon, it's just like we have the photon, okay, that goes with the electromagnetic forces. And we just thought, well, if there is dark matter, maybe there is another field of force with new bosons that come with it. So instead of being a photon, it would be something associated to a dark force. Not Star Wars, but dark force. And this dark force would come with the dark photon. So that's just the name that we gave to the boson associated with this new force.
Okay, thank you.
Thank you. Let's take another in theater.
Would there be a realm beyond the quantum realm?
A realm beyond, mon Dieu. You're asking a tough question. I would suggest in the hall there, in the atrium, there are lots of people with a yellow shirt. They're all theorists. No, this is really a question for a theorist. I'm an experimentalist. If you want a good answer, ask those people when you go out the room. And any of you have tough questions, please ask them. We don't know. We don't know what could come next. We're ready for the impossible.
So I'm going to have an online question. The question is, they mentioned how important diversity is, and it's improving, but there's work to do. What do you suggest could be next steps to help improve that?
You cannot just let things go on their own. I think you have to do really, you have to be proactive. You really have to go and look for other people. And what happens is that young girls are discouraged to do science from very young. Now we ask how come you're going to physics? No, and that's weird for a girl and all that. And where the boys are not asked those questions. And same thing if you come from if you're a black person and there are very few black physicists and all that. So we need to discuss these with students. If you have those discussions, why there is so little diversity, and then the young people see that there is nothing wrong with them, and they can all do something. And then the girls see that there's nothing wrong with them for wanting to go and do physics. And I swear, there's been no proof of any sort showing the superiority of men over women for the ability of making science. Same for superiority of white people over black people. I swear, I spent 19 years at CERN, and I have never seen a man use his genitalia to fix a problem. So, take my word.
Another question.
How did you first hear about this project, and what made you decide that you wanted to do it?
Oh, I was younger than you, and I had this idea. I wanted to know what matter was made of, and I was curious, and I first thought that chemistry would give me my answers and all that. And in 1969, when the first people went on the moon, and they pick up rocks there, and I thought maybe they will find new elements, new chemical. Man, no, it was the same things as here. So I was quite a bit disappointed. But I just always wanted to know what was there. And I had an unusual path. I was lucky to fall in love with someone who was in California. I moved there. She told me, but you have to get to do something. So then I went to visit SLAC, which was a big lab. And I was so excited about it, I just decided I would go back and study physics. And that's how it happened. But it was I don't know how I got that. I was always passionate about it. I think I will always be. It's very, very exciting to try to think, here at Perimeter Institute, the kind of ideas that they juggle with, about what will happen to the universe. Will the universe be there forever? Some theorists at CERN determined that we are in a metastable universe, and that in 10 to the 23 years it's going to explode. It's not really stable, but nobody will be there to see that. So it's just mind-boggling what science fiction has nothing to envy to physics. We deal with much better ideas, much more exciting ideas, I think.
Thank you.
One more question coming to the microphone. Thank you.
Hi, we all loved your talk. Anyway, I just wondered, when you're talking about the experiments and you look at the energy that's produced and the time it takes for the particle to disintegrate, what's the relationship between the time that they disintegrate in the particle? And I'm thinking in terms of like momentum, force times time, or mass times acceleration. So if a boson only exists for so long and it has a specific mass, is there anything special about the time they exist?
The more ways a particle has in which it can decay, then it's easier to make a decision. When there are very few ways to get somewhere, you hesitate, but you don't have many choices. So then these particles live longer because they don't have many choices. But when there are lots of ways in which those particles can decay, then they decay very fast. And so their lifetime is related to what we call their width, which roughly calculates how many possible decays are offered to them. And we try to calculate those things. Yeah.
What's the implication of that, though? Like, how does that affect how they behave? Or what
For
they
example,
do?
a Higgs boson can decay in all sorts of things. It can decay into leptons, it can decay in jets of quarks, it can decay into Z boson, into W boson. So there are a variety of ways. I was looking also, can it also decay into dark matter particles? So that was another thing that we looked at. So this one has a lot of ways in which it can decay, so it doesn't hesitate long, 10 to the minus 22 seconds, and it finds a way to go. So that's one implication, yeah.
Thank you so much. Ladies and
Thank you,
gentlemen,
Greg.
Dr. Paul Gagnon. Pauline Gagnon.